Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I would start just presenting the slides, and I hope that the computer will start working faster during the presentation. So what I would like to talk about is just some simple introduction how to use that toolkit that I am using for training recurrent neural network language models. And I would like for people to understand what to do, like just the most basic things and important things to get things done. So like how to train models that I want to show interactively here, like how to train models on some small data set like on the Penn Treebank, how to evaluate perplexity, how to compare the perplexity given by the recurrent neural network model to what, for example, RNNLM gives. That's like kind of standard implementation of Ingram models. And then some intuition how to do n-best least scoring. It's all very simple. Then I would like to speak a bit about how to train models on large data sets, as that is kind of a problem, I would say, because it takes a lot of time to train models efficiently, so people should have some experience to do it. And I would like to mention the most important things. And then I will show some, I hope that I will show some examples like with some more fun stuff, like for example some word vectors that were learned by the recurrent neural network. And I hope that it will be possible to show some interactive demonstration application. So that's basically the overview of the talk. It really seems that it will be quite hard to do it because speed is not good, but let's see. So the slides for this presentation should be shared at this link, so you can try to open it at your laptops, and there are also the examples that I will be referring to. So I will leave it here for maybe 1-2 minutes so that people can try to access it. It should be readable for everyone, so I hope that everything's okay. If you have Sigwin, it should be very easy to compile it. Just simply you need to go to the directory and type make. And if you are using Visual Studio for compilation of C code, then it should be also possible to do it. Just the source code, including some project solution, is in another directory, this RNNLM 03FMSVC. And here I'm just running that. What is it? Meeting isn't working.
Sorry, guys. Do you share this one?
Okay, so is it working?
It's not the phone that's ringing. I think it's your link that's ringing. Can you go back to the main? Shoot it. Cup of coffee. Maybe we're strange. This is supposed to be. Okay, so nice shot, right? I think everything can be working now, hopefully. This is one?
Okay.
Okay,
Yeah. Okay. So where was I? So I will still have this link for a while here, so that people can try to access it. And if anybody has some problem with it, then just let me know immediately, so that we can do something about it. But it should be possible for you to compile the toolkit easily and run some examples that I have there. So I can try it myself if it will be possible. Oh, it works faster now, great. So I'd frozen. Okay, so this is the shared directory, and it should be possible to go to this directory. Just yeah, so this is how to compile it. It should be very easy. So I hope that everybody has that link who wanted to see that. So now for the scripts. Is it working?
No, I missed the
Okay.
share name.
You will share this slides to us after
Uh, Yeah. And the slides are also shared in that same directory, and they are called RNNLM intro.pptx. So if somebody wants to access the slides, it is also in this directory.
Is this the same as the one you put in public on your homepage?
No. This is the slide that I did write recently.
No, the source code.
The source code. This is updated version of the toolkit that I did write during the internship year. There are a few extensions. So these are the slides, and then I have some example scripts, so I will go to it. So the first thing is how to train some basic model. The example script is in this directory, scripts 1-train. And you just need to run train.sh if you use Sigwin, or it will be slightly more complex if you will compile the toolkit using Visual Studio. Just you can check what is in the script, and it's basically just that it compiles the toolkit and it removes the model if it already did exist, and then it calls the last line where actually the training happens, which is here. It's not very visible, so it's not good. Well, basically I would like to say what parameters it takes. You just need to specify the training file, which is some text file. It is basically the same things as you would provide to SRI-LM. So I will show the text file if it will be possible. Yeah, it's working. So the data are here, and it's basically Penn Treebank data that I have from Johns Hopkins University, and it's basically just a sentence per line with all characters lowercase, so it's like normal stuff. Then after providing the training data, there is parameter for providing validation data that are used to control the learning rate. So no parameters are actually estimated from the validation data. Just the control, just it is used to control the learning rate, as we will see after I will run that command. Then there is a parameter that sets what will be the name of the model. Then it is needed to specify how many neurons will that neural network have in the hidden layer. Usually it is good to, if the amount of the training data is small, then it can be expected that even small number of neurons will provide good results, like 50 neurons can work well. But on large data sets, we would need like at least hundreds of neurons to get reasonable performance, which I will speak about later, how to avoid that, because with more neurons, the training takes much more time. Then the classes, that's quite useful trick, how to speed up everything about like 100 times. But it is completely automatic, so you just need to specify amount of the classes. It should be around square root of the vocabulary size, but it is good also to tune it a little bit if you want really to have good speed. That can be done manually by running several configurations and checking the speed. And then there are some parameters that control the backpropagation through time. Usually it's okay to run several times steps back propagation through time for computing the gradients for the recurrent weights. So it's not really needed to tune it unless somebody would really like to access some longer history in, for example, character-based language models. It might be good to increase the BPT steps to some larger value. Anyways, the unfolding of the recurrent weights is done after 10 steps. So even if just, for example, four steps are used for the back propagation through time, it does not mean that it just unfolds the network for the 4 steps, but it unfolds the network for 10 plus 4. That's for 14 steps after each 10 steps are processed. So it's not really needed to tune this unless somebody would really want to do something special. So I will run it to show how it works. So it shows the entropy on the training set, the progress, how many data were processed from the training set, and then the speed, how many words were processed per second. So it's like about 45,000 words. The training runs in several iterations. The amount of training data is almost 1 million tokens. That is words plus end of sentence symbols. The vocabulary size for this Penn Treebank setup is 10,000 words. It is automatically estimated from the training file, so the user does not need to do basically anything, just call the toolkit and it learns everything by itself. So everything that we had to specify were the text files with the training data and then the validation data. The entropy is shown on the validation data here. To get perplexity from the entropy, that's quite easy. We can take 2 power this number, because this number is basically bits per word. So if we would run a calculator, then, for example, entropy is 7.86 corresponds to perplexity 232. The model is saved during the training. I will show that the model is saved as I did specify by that parameter. RNN model hidden 50 class 100. So the model is here. It looks basically like this. There is some vocabulary in the beginning and some header with all the parameters. And during the training, it also produces a text file that has the same name as the model file, .output.text, and it shows like the probabilities and perplexities on the validation data. So we can see that it still decreases. After the perplexity will stop improving, the learning rate will become like divided by 2 at the start of each new training epoch. So that will produce another improvements, and after again no more improvements will be observed, the training will stop. So we can see that the perplexity drops with the constant learning rate till here, where the improvement is already too small. So the toolkit started dividing the learning rate by 2 so that the training still continues. So I will let it finish. It will stop like in maybe 1 minute. And this will learn a model with 100 classes and 50 hidden neurons. So it's by far not the best model that we can get, but it is a configuration that is reasonable to show during the presentation because it finishes in a few minutes.
You said the number of classes will be automatically detected
by the user actually. The classes are like words are allocated like assigned to classes automatically, but the user actually chooses the amount of the classes. So okay, so let's hope this is the last iteration.
So in terms of the time complexity, what's the relationship to the, for example, to the number of neural, number of the word? And the number of class, do you have some like big over?
Number of words like in the training data or size of the
So for
vocabulary?
example, the training time is linear proportional to the number of words for training. And it's probably quadratic to the number of neural, or it's more than that?
Well, I would say that it is a bit more complex, but training time is proportional to square of the hidden layer size plus hidden layer size times number of classes. Something. Okay. Well, this will be not visible for everybody. So I actually have this in a paper. So maybe I can open that paper if you want to see that. Okay, it will maybe take a while. So meanwhile, I can run the test.sh, which will run, which will take the model and evaluate the perplexity on the test set. So we can see that the perplexity on the test set is 162. And what it does, basically, it takes, it calls the toolkit here. It takes the model file, and then we specify the test file, and that's all that we need to do. So it's pretty simple. So that's the basic things. Now I will show here the answer to the time complexity. So the computational complexity for the recurrent neural network is proportional to this term, where I is the training epochs that we need to run, which is around 10 usually, but it can be less using some tricks. Like it is possible to get to like 6 or 7 epochs over all the training data to get good performance. Then W here is number of words in the training set. So it is like the more, if you have 10 times more words, it will take 10 times longer to train models. Then H is the size of the hidden layer. So if we have large hidden layer, then this term can actually increase quite a lot, because it is like a square of the hidden layer that represents the recurrent connections. In the feed-forward neural network, we have a very similar term that basically looks like this. Instead of H times H, we have H times this is basically the projection layer size. So that's also a problem there. And then this term is basically the H times V, where V is the size of the output vocabulary, and if we use classes, then we can change actually this to H times number of classes plus H times average number of words in a class. So something like this. So as I said, usually the fastest thing is to have a number of classes around square root of the vocabulary size. So the complexity would be something like H times square root of V if we use the classes. So I hope that this explains the computational complexity, but anyways, you can check that paper later. So that was for the training. I did also show the test phase, where we run this command basically. So we take the model and we run it on the test data to see the perplexity. I hope that's simple, and if somebody has some questions about it, then just ask me immediately. And then, of course, what we would like to know is if the model is good or not, and the easiest thing to do is to compare it to ngram. So we can do it here. This script will run the RNNLM tools ngram count to train a 5-gram language model with modified Nazarene smoothing. It will be open vocabulary language model because we have ANGs in the training data. It is possible to actually train even somewhat better ngram model by using all the singleton counts, like even using 3 grams, 4 grams, 5 grams that did occur just once in the training data, but it would take more time, so let's skip that. So I will just run it. It will train that ngram model, then it will take that NGRA model to calculate perplexity on the test data using debug 2 option using the SRNNLM tool NGRAM. And this is here, and then it will take that output file, which I will show now how it looks like. So the name was temp NGRAM. So this is the, many people probably know this output. So this is the output from SRNNLM. With the debug 2 option, we can see that the perplexity of the test data given by 5-gram model is like 147, and we have even probabilities for each word, which are these are here. Okay, so now I will have to wait until the network will start working again. Okay, fine, and then we can convert this text file to get just the probabilities of words using a simple tool. That is done here, and then we can take these probabilities that look basically like this, like it's a probability for a word at a line. So basically it's this column saved as a text file, like just for the word. So we have here like 0.002. We get the same here. Okay, will it open? No. Yeah, it's a little bit more difficult than expected. Yeah, so it again did freeze. Yeah, okay, so it's again here. So yeah, so this is basically the probability. So that's what we can give as a parameter to that RNNLM toolkit, together with the weight. 0.5 means that linear interpolation will be used to compute the combination of that RNN model and the NGRA model. So I will just show what was the output. Okay, here it is. So the perplexity given by the recurrent network model was 162. By the NGRA model it was 147. The combination linear interpolation of these two gave perplexity 127. So we already get some good improvement over the baseline NGRA model, even with model that was trained in like 4 minutes. But it's possible to get much better by using, for example, more neurons.
Is there a way of increasing the font size there?
Oh, yeah, it's not very visible. You can options.
Do you know anything on your big machine? Why it says
No, I don't do that or anything. I think that just the network is kind of not so good. Okay, yeah, is it better? Yeah. So as I said, the perplexity given by the network was 162, given by the NGRA model was 147, and the linear interpolation gives 127. So, of course, that's not the best we can get. We would be able to get better results by using more than 50 neurons, and so on. Mainly the hidden layer size affects the results quite a lot.
Do you ever train on more than a single machine, or is this always single core training?
I train on single core only, because I think that's the best thing if you want to have some general purpose toolkit that will be easy to share with other people.
Is it possible to do something like averaging of parameters? Could I train on different subsets and mix the parameters?
I know that people who train acoustic models with deep neural networks do something like that. I have seen something like this. But for the recurrent neural nets, I am not so sure that it would work. I did try something like this, like what you said, like training on different subsets, sharing the parameters later. That didn't work.
Don't you have to find some kind of a correspondence between the different nodes? I mean, they might not mean the same thing.
Yeah, I don't know.
One run versus another, so
yeah.
it would be scary to me.
Yeah.
But imagine you initialize for a while and then split it apart and periodically mix parameters or something. I don't know. Just
So that it would naturally over the course of time, the nodes would come to mean the same.
say say I did several rounds of optimization on some portion of the data, and then initialized 10 seed nodes and let them climb from there for a while, and then mix those parameters back together.
I
and
see.
did some more optimization.
Oh, so they get the meaning from the fact that they're all initialized from the same thing.
Exactly,
Okay.
and then you do a little bit of mixing at the end to make sure all the nodes are brought back into some correspondence at the end. I'm trying to figure out some way to make this. I don't know how time works, but I'm just.
Yeah, so I think that's a good idea. I did try something like this before, but it seems hard to make it working with recurrent neural nets because they are kind of sensitive even to small changes during the training.
Okay.
So, yeah, so one of the practical advices that I would have is that I usually need to use double precision of float numbers during training. If I use like more than small amounts of data, otherwise the training can even diverge. So just the 32 bits is not enough for float numbers. But after the training is finished, the model is quite robust, so the precision is not needed anymore. And
That's interesting. Does it have anything to do with the backpropagation over time distance?
I think that it is related to the gradient distance training, where you do a lot of updates,
Yes.
and if you do small mistake at every update, then it adds up over time and it can do some problems. So you can actually use some batch sizes like that. You would do the updates less frequently, but then it degrades the accuracy, so you obtain worse perplexity. So it's like kind of trade-off. So yeah.
Does it worry you that batch works worse than stochastic? That makes it feel like to me that you're not optimizing the right objective.
Well, I think that it works worse almost for everyone. The batch.
So if I
than
tune a
stochastic.
Maxent model, not for language modeling, but just in general,
Yeah.
then batch generally works better than stochastic.
Yeah, for Maxent it is somewhat different because Maxent can be like convex. Yeah. While with neural nets you have this nonlinearity, especially with recurrent neural nets you have nonlinearity applied many times, so it is much more difficult optimization problem. So I would not expect that it can work well with batches. It actually several people tried it already before to train recurrent neural nets with batches, and it seems to really degrade performance, like for not just for me but even for other people. So yeah.
The numbers you're presenting here are perplexity on a held-out development set or test set, right?
Test set it was right
so
now.
What happens if you compare batch versus stochastic on the training set? Is it the case that batch fails to fit well on the training set?
I usually look at the validation set perplexity.
I understand.
So I'm
but
not
it feels
sure.
Like that's a different thing, right? I mean, is batch?
Yeah,
It could be that
I
batch
mean
is
that I am not
overfitting.
sure if it works worse on training set or not. I would have to check it. Yeah, it works worse on the validation than test sets. So like this. So that was for the combination. I will get back to the slides. So yeah, here it's just written what I did say now. So for the n-best lizard scoring, it's also kind of easy to do things. I have like an example here. We can have some n-best list that will look like this, that we have like two sentences with first sentence is like 4 hypotheses and the second one has 2. And the n-best list format that I take for for the toolkit looks like this. So we have unique identifier at the start of each sentence that basically says that this belongs to the same set and this belongs to the same sentence. And then is the sentence, and the toolkit will produce the log 10 probabilities of all these sentences. So I will show it here. So that text file that I did show before looks like this. And if I will run the command, it will produce the log probabilities. So it looks like this, that we just specify the model, then we specify the NBEST file using the test option. Then we say that it will be actually containing NBEST list, so that means that every sentence will have unique identifier at the start of the sentence as the first symbol. And the debug 0 means that we are just interested in seeing the log probabilities at the output. So this can be used easily for NBEST list rescoring, so people can generate some kind of NBEST list by themselves for any task, like it can be speech recognition or machine translation, and get the probabilities from the RNN, and then combine these probabilities with, for example, acoustic model score or other models, like in machine translation, like the phrase translation model and so on, and then do the NBEST list rescoring by picking actually the one best using the new language model scores. So actually the old language model score does not have to be replaced, and people can tune the weights. But usually when the RNN language model is reasonably large, it seems that it works well by itself, and it's not really that much important to combine it with the Ngram model, especially if the model is trained together with the maximum entropy model, as I will show later, because that already contains some kind of Ngram model in itself. So that's what I will show here. We can train some simple maximum entropy model with the toolkit as well, because it's a very similar thing. We will be training it by stochastic gradient descent, so it's a very simple thing. It will not work terribly well, but it will work. So I will show how it runs. So for training, the parameters that we have to set are here. So that, it's basically the same thing as when I trained the recurrent neural net. Just I set the number of hidden neurons to be 0, and I choose these two additional parameters. Basically, I say that I will be using Ngram features up to 3. That means that I will be using unigrams, bigrams, and trigrams. And I will allocate 10 million parameters for the hash array that will contain all the parameters. So that's basically some very simple implementation of maximum entropy model. So we'll train some simple trigram with some limited amount of parameters. It runs faster than the training of the recurrent neural net, of course, because it's just a maximum entropy model, but it uses the same training algorithm that is like the stochastic gradient descent. So even if it can be seen as the convex optimization problem, and it's definitely possible to train this model much faster, the point is that if we can train the model in the same way as the recurrent neural network, we can train later the models together, which I will show in the next example. So let's just let it finish. So there's some difference in the speed. When I was training the neural network, it was like able to process about 45,000 words per second, but for the maximum entropy model, it is like 3 times faster, because it's much simpler model, of course. I have this also like explained in my thesis, like how it works, like from the scientific point of view. Here I'm just showing how it like runs in practice. So it's already finished. Yeah.
So just on the maxent part,
yeah,
where you specify the number of features,
yeah,
is it keeping track of hash collisions, or is there some implicit parameter tying?
No. The collisions are not solved at all, because simply it expects that if you will use a large enough hash, then the number of collisions will be small. So it is like more optimized for the speed, because if you would be solving collisions, it would be slower.
And when you change it like from 100 to 1,000 or something,
yeah,
will it go through and do some kind of a pre-computation step and figure out the most frequent n-grams in the training data and then create features for those, or does it just always use all the n-grams that it sees?
It uses all the n-grams as it sees, like it does not do anything special. As I said, like the motivation for this implementation is that it's very, very simple, and like it would be possible to write it in C code, maybe on, I don't know, like just the training and test phases, maybe on 10 lines. So like this is like the reason. It would be possible to make it better, but anyways, we want this model just to be able to capture some n-gram patterns, and then we will be training it together with the neural network. The neural network will learn the complementary information, so I think that even if some improvements are still possible to this implementation, it would not be something like dramatically different than this. So just show. So the perplexity is worse than given by the n-gram model, which gave like 147, but that was 5 gram. This is just 3 gram with 175. Then if I will combine them, then because the max entropy model uses classes, so it is even like somewhat different than the normal n-gram model. So it actually even gives some small improvement, but here it's not very significant. Interesting thing is that if I would use a lot of training data and large size of this hash array, like something like direct 1,000 or 2,000, then it actually starts giving quite complementary information to the n-gram model, and basically it is very similar to model M in some sense, just that it's much more simpler, and like I don't even tune much the regularization there and things like this, because I don't think that it's that much needed on large data sets. So
you have a constant regularization? It looks like
yeah, I have some small L2 regularization, and I don't think it's very important. Basically, I use it because it's important to have a stable training for the recurrent neural network.
It's also important for maxent, because maxent can diverge in the absence of a regularizer.
Yeah, if you use stochastic gradient descent, it never happened to me.
Okay.
So.
And you don't seem, so even though your data set sizes can change significantly, it doesn't seem necessary to retune that regularization parameter?
No, not for me. Yeah.
Have you tried tuning it?
Yeah.
On different data set sizes, and it just doesn't make a difference?
No, as I said, the only reason that I found that it's useful is that it helps to avoid this problem with divergence during training of RNN, but otherwise I would not really need it. So yeah, I think it's really different if you train something.
How's the step size that's used? Is it the same step size for the maxent parameters?
What's step size?
So when you compute the gradient,
yeah.
How far in the direction is the gradient?
Yeah. That's controlled by the learning rate, and it's the same for the maxent as for the RNN.
And for the regular.
Yeah. So actually the point is that I wanted to train some kind of n-gram model in a similar way as I trained the neural net model, so that I would be able to train them together, as I will show here. So I have it in the slides. Okay, so just to say, so that was using 10 million direct parameters, and after the training finishes, the accuracy is not really that important, because I mean of each parameter, and they can be quantized to some very small size, while the perplexity will remain basically the same. That's the advantage of that hash implementation. So the next slide is training of a recurrent neural network and the max entropy model together. And here I will show that actually on the Penn Treebank it does not really give much advantage. But what I did show previously is that on large data sets this is kind of crucial thing to get good performance. So because in there we have to limit the size of the hidden layer, so let's just train it. Meanwhile I can show things from my previous presentation from last week, where I have this shown. Yeah, let's hope it will open. Well, again, the network seems to be broken. Well, probably we need to wait. Okay, so what I wanted to show is that if we train this neural network together with maximum entropy model, then on this Penn Treebank data set, we will obtain better perplexity quite a lot than if we would train just the neural network with the same parameters, like number of the hidden neurons. But after interpolation, actually with the Ngram model, the results are about the same for the neural network or for the neural network that is trained together with the maximum entropy model. But on large data sets, it is different because we can get much better results there, and the explanation that I have is that the neural network, especially on the large data sets, can focus on learning complementary information to the Ngram features, so that if we have a limited number of neurons, it can learn much more things than if it learns separately from the Ngram model. I also show in a paper that these Ngram features, these maximum entropy model features, can be seen as a neural network that has just input and output layer, basically something like logistic regression. So the whole model can be seen as one big neural network. So it seemed to be working, but again it's frozen for a while. So, okay, will we do something? So if somebody has some questions, we are waiting now, and just you can ask. Yeah, it seems to be doing something slowly. Yeah, I want to go to like to slide 50 or 45, something like there, to show some graph. Yeah, here it is. So I would stop moving now. Okay. So this is what I wanted to say. If we have like small amounts of data, then the difference between this neural network and neural network that is trained together with the maximum entropy model is not that large if we are not looking at just the perplexity of individual models, but at an improvement that we actually can get over Ngram model. So the Ngram model performance is like at the 0, and here we have like improvements like in bits per word for these models, with some small amount of neurons in the hidden layer. So we can see that if we have like 1 million of training words, then we don't really get much by training neural network together with this maximum entropy model features. But if we have like large number of neurons, then the difference is actually quite large. And yeah, it seems really like crucial thing to train the neural network together with some direct connections between the input layer and output layer if we want to have good performance on large data sets, because there in practical cases we always need to limit the number of neurons that we can have in the hidden layer because training model with 2,000 or 3,000 neurons is just not doable, at least not today.
So the interpretation of this is that the Knaser-Nye model,
Yeah, that's the baseline. That's like 0.
is able to do well when you give it tons and tons of data. And that's why some of those lines go
Actually,
up
the,
over to the
the
right
explanation
instead
is
of
that
right.
as you increase the amount of the training data, then these models are like providing smaller improvement because they have like fixed number of parameters that are in this.
Okay. Whereas
you know,
the Knaser-Nye number
yeah,
of parameters is
while-
going way up.
Yeah,
And
the
that's why.
baseline model is getting much larger, while this one is like kept constant, like the hidden layer. So, of course, even the input and output layer here can increase if you change the vocabulary, but the number of parameters that are like associated to these time patterns are like constant. So it is really like, as I said, the problem with these models is that we know that if we would use more neurons as we increase amount of the training data, that we can get better and better, and actually at some other graph that I will not search for because it would take too long. Yeah, I show that if we increase the amount of the training data and if we at the same time increase also the size of the hidden layer, then the difference between the neural network language models and the Ngram models is increasing, so we can get much more on large data sets. But the problem is that this is nice, but if we use very large data sets, then we would need to use very large hidden layers, which is not doable. So the whole point is that we can use small number of neurons and still get good improvements from Ngram models, from neural net models, as long as they are trained with some features that are similar to Ngram models. So I will go back to the examples. I hope. Yeah, so the training finished, so I can run the test, see the perplexity on the test set. So before it was like 162 for the neural net model, now it is 141. So it seems that it improved, but as I said, after I will combine this RNNLM model with the Ngram model, it will be not really better than when I combined before the neural net model with the Ngram model. So before I had like 127, I think, now I had like 129. So this is what I was actually showing just now at that figure. Like if I have small amounts of data, then this trick does not seem to do anything. Maybe I would need to use better the regularization or something, which I did originally, and on this data set it would work better. But I did not like to tune this regularization parameter because on large data sets I found that it's not really needed. So I will just try to speed it up because it's already 12. So another example that is very simple. We can generate randomly some data from the model, like we just specify the model file and then the amount of tokens that we want to generate. So it will look like this. It's basically some word that probably everybody knows what sampling of data means from this probabilistic models. Actually, the same thing can be done even for example, character-based models. Like people can train character-based recurrent neural network model using this toolkit. Like just the only thing that needs to be done is to split the training data that normally look like this, as I was showing before, to some individual characters, something like this. And like each character is now like a word, and we can train recurrent neural network on this, on these characters, and then we can generate like new sequences of characters, which will be looking like where we can see actually some new words generated and so on, like all these things. And the last interesting example that I wanted to show was this one, so let's just run it. Here I have some word projections that are obtained from a neural network that was trained for a broadcast news task. It was trained on a lot of data, like more than 300 million tokens with about 87,000 words in the vocabulary. And the thing is that we can save the matrix between the input layer and the hidden layer. And for each word, we have associated as many parameters as we have neurons in the hidden layer. And we can treat this vector as some continuous representation of that word. And this way we can search for similar vectors, and we believe that this neural network, after it is trained, will be able to assign similar words to similar space, so that if we will search, for example, for vectors that are similar to vector that is associated with Monday, it should give us some days in the week, and it actually works. So yeah, so it gives like Tuesday, Wednesday, and so on. So I can write there like something else. Maybe somebody can say something, like some word, and I can try.
Bank? No.
What? Bank?
B-A-N-K, the famous bank.
Bank, okay. Okay, so it gives some similar words.
How about force?
Force? Force is pressure on
Pressure in the
yeah. Mm.
How about friendly?
Unfriendly. Yeah.
You will try apple? Apple.
Apple.
Apple, like the
Apple.
fruit or the computer.
Ah, okay. So because it is trained on the broadcast news data, it will be not a fruit, but it will be like companies.
Pumpkin there.
Not pumpkin is there as well.
Why is
I think these are all big corporations.
Yeah.
Corporations or advertisers.
And some fruit.
Microsoft.
Why does turkey show up?
Like,
Is Thanksgiving?
Turkey with apple pie.
yeah. Mm.
Interesting association.
So in your training language model, when in your training you define, say, 100 class,
Mm.
and then you assign word to class. How does this work?
It works based on the unigram frequencies of words.
So you cluster the word.
So it's like frequency binning. So you want to have many infrequent words in one class because you know that you will be evaluating them like very infrequently, while you want the frequent words that you expect that will be evaluated frequently to be like just in a single class, like just by themselves, like that they will not share the class with anything else, because you know that you will compute the probability for this word frequently, so you don't want to have that class to be large.
So the word in the same class have no connection, have no semantic
No.
connection.
That was actually the motivation when this kind of trick was introduced by Benji and his student, like when they used this kind of multi-level classes to speed up training of these neural network language models. They actually tried to use some WordNet to assign similar words to the same classes. But then I found that actually you don't need to do anything like this, and you can just use unigram frequencies and it will work good.
So do you try random, just random pick?
If you were to do it randomly, then you will mix like frequent and infrequent words, so it would be much slower and also worse. So that's not good.
Consideration about defined classes is pretty much for speed only.
It seems so. Like it is possible that you can still get somewhat better results by using some classes that would actually cluster similar words, but you see that from using classes you lose not so much in the perplexity, so you know that you don't have so much to gain. Okay. So yeah, like it can be done better, but things would get more complicated, and it's not really clear if it would be that much useful.
Okay.
Yeah, so that's all the examples. If nobody has some other word, then...
Yeah, I have another question for this kind of example, because I saw this kind of, example in topic modeling, in clustering by LSA. They all show the same, but how can I tell which one is better?
Yeah, it would be good to actually do some comparison where we would have some real numbers, and we are actually thinking about doing something like that, where we can evaluate quality of this. So yeah, we will try to do something.
Another question. So when you calculate the neighbor, the nearest neighbor, you use just a Euclidean distance.
It's basically cosine distance, but it's very similar. Yeah,
Okay.
it's very similar. As
People try a different distance or just arbitrary distance.
I think that
Because when you
they
train it, you didn't enforce any distance. Do you enforce or either explicitly or implicitly when you train it? Do you enforce any distance measure?
Yeah, I think that people before used also just simple distances, but I'm not so familiar with what they did.
Yeah, with something like LSA or LDA, with LSA at least, you have no guarantee that your vectors are going to add to 1 unless you explicitly, after the fact, normalize them, which is part of the cosine distance metric anyway. So.
Okay. Yeah, for example.
Well, we believe that this works. The neural network works for like finding similar words much better than LSA or LDA, but we need to prove it. So we are thinking about doing some tests.
Okay.
So yeah.
Because one simple way you can say, okay, even you can think it's look like a multinomial dimension, multinomial distribution. Each element is a probability. So you can even use scale distance. I mean, there are all kinds of hypotheses. I just wonder if there are any distance enforced even explicitly in your training process, because the best distance shall be the one matched with your training implication.
Yeah. So we are somewhat working in this direction. So let's see.
Okay.
Yeah.
Okay, cool. I think we.
Yeah. So somebody has some questions. I wanted in this talk mainly to introduce the basic things like about the toolkit so that people would be able to use it in some practical applications. So I hope that it does not look complicated at all. And if somebody has some ideas how to make things maybe simpler or so, then just let me know, because I think that this is really simple to do.
You have done one experiment. So you have the RNNLM, which is not easy to directly input in the decoder.
Yeah.
But then you said you train another model, can look like RNNLM, but in an n-gram format. But you try it in the decoder.
Yeah, actually it's possible to, as I was showing these generated data, like that's an interesting trick that we described before. We can actually generate the data from the neural network model, which I did show here, which seems like we can see basically what the model was able to learn from the data, because if it would be able to learn the language, it would look very good. We can generate the data also from the n-gram model, and we can see that there is quite a big difference, as I showed at some examples. If we train a really good n-gram model, neural net model, then it has not only better perplexity, but it also like produces much more meaningful text. But we can also produce a lot of these sampled text from the neural net model, and we can train then n-gram model on top of huge amounts of these text that was generated by the neural network, and it can be seen as some conversion of the neural network to n-gram, because we can actually think about pre-computing all the frequent n-grams using neural network language models, and this is similar to this. Like if we will generate a lot of random text that follows this distribution from the RNN model, and then train on top of that the n-gram model, it will kind of approximate that neural network, and we can get some perplexity reductions, and it works even for like say word error rate reductions in speech recognition and so on. And then you don't need to have in the decoder the neural network. You can have just the neural network to be approximated actually by the data. So the only thing that changes then is the data. So you use different data.
But isn't that strange? So even the neural network can generate a very good text. It's still worse than the true natural text, right? So I like want to learn from the true text shall be still better than the learn from the RNN.
Yeah, because you use it as additional data actually.
Okay.
So you mix it with the n-gram model trained on the true text, plus then you train the neural network on the true text that you use the neural network to generate even other likely combinations of words,
I see.
and train NGRAM model on top of this, because you can see that neural networks can do all this clustering. You can see that if you see, for example, Monday in some context, and then you have some unseen context where was, for example, Friday, you would want to compute its probability, but because you didn't see it in the training data, you will assign it some small probability because you will back off. But if you will generate huge amounts of text data from the neural network that was already able to cluster Monday and Friday, so it can generate actually something in the same context, like where Monday was seen, it will generate something similar with the Friday, so you will be able to get this pattern this way.
Okay.
Yeah. So
any more questions? So how about we just stop here?
yeah.
Good. Thanks.
Yeah, thanks.